Alright, hello again, welcome back. I want us to have a look at direct current DC circuit theorems and current source and EMF. Now what I'm hoping to do is for us to look at and go into the Thevenin's theorem and circuits with an applied EMF in the circuit. Now what I wanted to do first is to look at what an EMF is, and that you know what that is. It's simply a voltage applied to a circuit. Okay? It's an electromotive force that drives electrons around the circuit. Now remember that in regards to electrons, they flow from negative to positive. But remember that the conventional flow of current is considered to be from positive to negative. Okay? Now an EMF, denoted E or E, is an ideal voltage source with no internal resistance. That means that you've got a voltage but there is no resistance to that voltage. So you can say if the voltage is 9 volts, then you're going to have a 9 volts output. But we know that cannot be the case, because in any flow of current in a circuit, you will meet some sort of resistance, no matter how small that resistance is. Okay? The fact is that we need to take that resistance into consideration when the voltage is applied and the current that we wish to have flowing through the load. Now the current depends only on the load connected to it. Okay? And that is the current that will be flowing through the load. But in order for that current to flow through the load, we need to take into account all the resistors that makes up that circuit. Now, sorry about that. Remember, it is the ideal not to have an internal resistance. Okay, it is only the ideal. It does not exist in the real world. There will always be some form of resistance. The issue then here is how do we get around that resistance, and how do we calculate that resistance in order that we get the optimum current flowing at the output stage that will allow us to drive whatever load we choose to put onto that circuit. So let's look at how that comes about. Thevenin's theorem. Okay, now obviously some of you will be able to pronounce Thevenin's far better than myself. I have a problem getting my tongue wrapped around Thevenin's. Okay. Now Thevenin's theorem is used to simplify a resistance network with voltage and current sources within it. We replace the network with a single EMF, E, and a resistance RT in series with it. Okay. This is like replacing the network with a battery that contains internal resistance. The following diagrams illustrate the equivalent circuit. Okay. Now again, you must draw out the diagrams as they are given. It enables you to understand the concept as to what we're trying to say in a diagrammatical form rather than just verbally. Draw out the diagrams. Put in the information. Don't just assume that it is there to look pretty, or it is just there for my good looks because I'm handsome and debonair. Okay? Now in diagram T1, resistor R1 is in parallel with resistor R3. This is the parallel network that needs to be calculated first. Okay? We now need to show the calculations and the equivalent circuit after the calculations has been done. Now A and B is open circuit. This is where the current source would appear and the load resistive or otherwise be connected. Calculations first to resolve or solve the parallel circuit, and we're going to use the formula which allows us to take into account two resistors in parallel, and that is Rp equals R1 times R3 over R1 plus R3. Now this is referred to as product over sum. Once we have found the parallel network, the value of the parallel network is then added to R2. So we need to have a formula that shows this and brings this into play. And what I've done here is to show a formula of RT equals R2 plus R1 times R3 over R1 plus R3. The following diagram shows the equivalent circuits and relevant calculation formula. This is the equivalent circuit for diagram T1. Now again, draw the diagrams out in full. Do not leave out any information. This diagram T2 shows you the equivalent circuit, which represents the simplification of the resistors in T1. Thereby, this indicates the parallel resistors calculated added to R2. Okay, now you will see how that is done as we go on further, but I thought that it was appropriate to show you the results in regards to the equivalent circuit for T1. Now we have here RT equals total resistance of the circuit, E equals the applied EMF, A and B the output. To determine RT, we evaluate the resistance as seen at the terminals A and B, with the voltage source replaced by a short circuit, as shown in diagram T2. And that's diagram T2. Okay. Now, current sources are open circuit. The voltage that appears at A and B is constant, so the current drawn would depend on the load applied across A and B. Let us look at the calculations required to deduce the network. Okay. We need to calculate the parallel resistors first. Rp equals R1 times R3 over R1 plus R2 plus R3. Apologies. The next stage will then be to bring R2 into the equation. And here we have brought RT into the equation. RT equals R2 plus R1, R3 over R1 plus R3. Okay? This gives us the total value of the resistor that will make up the circuit as a single value resistor. This can be seen in diagram T2. Let us now look at the circuit as a whole. Taking into account current, voltage, and where there is a current flow, this diagram shows you the voltage source, direction of the current, and where there is no current flow, because there is no current flowing through R2 at this point in time. The current will only flow through R1 and R3. Okay. Now I've now gone on to do the calculations which should give us the results in regards to the voltages and the current that will be flowing in the circuit. So I equals Vs over R1 plus R3. E equals V open circuit, VOC means open circuit, equals I R3. E equals R3 times Vs over R1 plus R3. E is the voltage that appears as the input voltage, taking into account the resistance in the circuit. It would be the voltage appearing across R3 as measured at A and B. Okay. Now let us look at an example. I will take it step at a time. With example 1. Okay. For the circuit shown, find the values in Thevenin's equivalent circuit. If a load of 10k ohms is attached to terminals A and B, what is the current drawn and voltage? Now what I'm now going to do is draw a diagram to represent the circuit that I'm talking about and to understand how I need to evaluate the resistors that are in parallel. And again, we know R1 and R3 are in parallel. And this is diagram 3. Okay. Again, you must draw out these diagrams. Do not take it for granted that you know it or you can glance through it. You cannot glance through this. Okay, write it out. What the hands has written, your brain does not forget. Okay, how to apply the solution. Now what I want to do here is to just make some little notes. We determine the parallel circuit first. This will consist of resistors R1 and R3. We apply the formula as previously given above. Okay? And these are our formulas. RT equals R1, R3 over R1 plus R3. We now bring these values in and insert the values as we have been given them. Okay? Sorry, I'm drifting off a little bit here. Okay. Right. Now RT equals 11,000 times 47,000 over 11,000 plus 47,000. That gives us 570 million divided by 11,000 plus 47,000. Now I've then gone here on this here. You can put it into your calculator as such as 517 times 10 to the power of 6. Okay. Now that then equals 8,913 ohms, or 8.913 kiloohms. Now remember, when you're dealing with large values, you must put these values into what's called standard form. If you don't know what standard form is, look it up. Ask your lecturer. It is the 1 to the power of 6 or 2 to the power of 4, etc., etc. Okay? We now add these resistors together. 8913 plus 22,000 equals 30,913 ohms. But let's bring that down to kilo ohms because we're dealing in large values. It's 30.913 kilo ohms. Okay? Now, so we now have the total resistance of the circuit, but remember we were given a load of 10K, so this has to be added to the total value. So it's 30.913 kilo ohms plus 10 kilo ohms equals 40.913 kilo ohms. Remember, the load is across A and B. We now need to find the voltage using the formula. E equals R3 Vs over R1 plus R3, which gives us 47 times 12 over 11 plus 47. Now please remember, that is 47,000 and 11,000 plus 47,000 times the 47,000 times 12, which represents the applied voltage. And when we put that together, we get 564,000 divided by 58,000. Comes out to 9.724 volts. Now do this for yourself. Do not just look at it on the screen and assume the figure is right. I may have made mistakes. I can be wrong. I might not be able to add 1 and 1, which makes 2. So I might get it wrong totally. Put it into your calculator. Recheck it for yourself. Confirm that and be sure that you're happy that the result I have given is correct. We know I equals V over R. I equals 9.724 volts because we have been given the voltage already. We know the total resistance is 40.913 kilo ohms. That will, when divided by that and you put into your calculator, you should get 2.37 times 10 to the power 4, which will be milliamps. 2.37 times 10 to the power 4, which will be amps. Moving it to milliamps, 0.238 milliamps rounded up. Okay, and that will be the current. Now again, make sure you have arrived at these figures for yourself. Put them into your calculator. Make sure that they work out. So remember that your calculator, some of you have calculators which goes to 10 digits, 12 digits. Some of you may even have calculators which goes to 14 digits. So remember that the larger amount of digits you have, the more accurate your figures will be. So allow a round of figure, common sense application, I should say. Okay. We know that V equals I times R. V equals I times R, so it's 0.238 times 10,000. Now, because it's milliamps, 0.238 milliamps, I'm going to remove the 3 zeros that makes up the 10,000, which will leave me 10. So when I multiply 0.238 times 10, it will give me 2.38 volts. It's just a shortcut I've taken. But some of you will look and see what I've done, and please apply. Make sure you understand how we have arrived at 2.38. Do the working out for yourself. It will be 0.238 times 10 to the minus 3 times 10,000. It will still give you 2.38 volts. Remember, it is 0.238 milliamps. A milli is 1,000. So if we remove 3 zeros from the 10,000, it will leave us with a numerical 10. When we multiply 0.238 by 10, it gives us 2.38 volts, or you can just multiply it as we did above. Oh, okay, sorry, I'm leaning out a bit. Thank you. Okay, it appears that is it for today. Thank you for your time, and please take the time to draw out the diagram. Listen to the information, read the information for yourself, write it out. Do not assume that you know it offhand or you will remember it. It will not work that way. Okay, I think we can bring that to a close now. Thank you, and please do have a good evening. Okay.